All right, we have a area volume problem here. This is what I classify as type 4, and it fell on the 1999 test, the no calculator portion. And the graph is y equals x squared, parabola, and a horizontal line at y equals 4. The shaded region is bounded between those two things shown in the figure above. Classic problem, type 4. Part A, find the area of R. So when you're finding the area between two curves, the general idea is you take the top curve and you minus from that the bottom curve, because the idea is that you're going to take the area under the line and subtract the area under the parabola, and that will give you the total area trapped between the two. So as we draw rectangles, this is rectangles that are stacking up along the x-axis. So it should be pretty easy to tackle this with respect to x. So we take the integral of the top curve minus the bottom curve with respect to x. And we need to identify the boundaries that occur. And the boundaries are not explicitly stated on the graph. So when we try to find the boundaries, the typical approach that shows the work is you set one equation to equal the other equation, and this is to find your intersection points. This is a fairly simple equation to solve. 4 equals x squared. If you take the square root of both sides, you get 2 is equal to the absolute value of x, or plus and minus 2 is equal to x. So we now know our upper and lower boundaries for the integration problem is from -2 to 2. There's the integral to set up. If this were a calculator active problem, I would go to a calculator and type that in, but being that it is a no calculator problem, we're going to take the antiderivative, x to the third over 3, and then evaluate it from -2 to 2. And what this means is we're going to plug the 2 into it first, and we get 8 minus 8/3, and subtract from that, plugging -2 into it, which is -8 minus -8/3. And this is a numerically correct answer here. And once you're to a numerically correct answer, you should stop so that you don't make any mistakes with simplifying. However, for the sake of the video, I'll go ahead and simplify this out. The 8 and 8 combine, and the 8/3 comes together, and we get a total of 32/3. So the area enclosed is 32/3. If you wanted to do a little bit of a rough check for accuracy of this, you could say that you have a rectangle that is 4 units tall and 4 units wide. So the total area is going to be something less than 16, because a 4x4 rectangle would be more than enough area. And this number is in fact less than 16, because 48 over 3 equals 16. So we're less than 16. When it comes down to points accumulation for this AP question, you would get 1 point for setting up the integral correctly, and then 1 point for finding the correct evaluation. All right, moving on to part B. Part B is a volume problem. We're going to be revolving this region around the x-axis. So I've created this sketch here to just kind of visualize what this will look like. This is the 3D coordinate plane. You've got the graph of x squared, and then the line y equals 4. And what's going to happen is we're going to take this region here and rotate it around the axis, specifically around the x-axis. And if we take a representative rectangle, we can picture the idea of that rotating around the axis, and it's going to create the shape of a washer. And so this is how I know that the washer's approach is the approach that I'd like to take. And the loose general form for washers is pi integral big R squared minus little r squared and they're stacking up along the x-axis, so dx. So I created a little second drawing here to kind of visualize what that washer looks like, and the distance from your rotation line to the outer length is considered your big R of x, and the distance between your rotation line and the inner portion of the ring is considered your little r of x. So for this particular function or region, big R of x is going to be outer boundary minus rotation line, so 4 minus 0, and then our little r of x is going to be our inner boundary subtracted from a rotation line, which is going to be x squared minus 0. So then what we're going to do is we'll stack up several of these washers, and if I take the volume of a single washer, which is going to be the idea of pi big R squared minus pi little r squared times the width of the washer, this is kind of your outside edge minus the hole in the middle of it times the width. This would be the volume of a single washer. And that width tends to be considered your differential. So that width is dx. It goes from delta x to the infinitesimal size of dx. So what we can do is write the volume is equal to pi times the integral of big R of x squared minus little r of x dx. And those washers again stack up from -2 to 2. And we have our volume equation. And sometimes we can get away with just writing the volume equation. On this particular problem, they actually ask us to evaluate the integral. So to find the volume, we're going to have to do the calculus. So volume is pi. The antiderivative of this integrand is 16x minus x to the 5th over 5. And that is going to be evaluated from -2 to 2. Then we want to plug in our upper boundary into the antiderivative and our lower boundary and subtract the 2. So we have pi times the quantity 32 minus 32 fifths, subtract -32 minus -32 fifths. This is our numeric answer and will be entirely sufficient to get credit for the problem. If we went through the route of simplifying the expression, it reduces down to 256 pi over 5. The point breakdown for this problem is worth 3 points. And your first point is for having the constant in the limits. So pi and the -2 to 2 is worth 1 point. You get your second point for having the integrand correct. So the 16 minus x to the 4th is your integrand. And then finally, your last point comes from, did you correctly evaluate the integral problem? So those are your 3 points. When we move on to part C, what we're going to be doing is the same process of revolution. However, our revolution line has changed. So instead of rotating around the x-axis here, we are doing a rotation around a line K. And specifically, that K value is larger than the line 4. So our washers now are starting to look a little more like that. Right? So the approach is going to be the same thing. We have pi big R squared minus little r squared. We're just going to redefine the difference between our big R and our little r. So when we establish our new big R for this problem, the outer radius of this red washer would be the distance from x squared to k. So our big R of x in this case will be k minus x squared. And then our little r of x would be the distance between the line 4 and the line k. So little r of x is equal to k minus 4. Okay. So all we have to do is find the equation that models the volume using these two radiuses. So our new volume, I'll call it volume 2, is pi, the integral from -2 to 2, because our boundaries are not changing, of big R squared minus little r squared, and then the width of the washer is your infinitesimal of dx. This is the volume for this red region when we stack up all of the washers from -2 to 2. And the question was to create an equation where this volume was the same as the volume found in part B. So to get the correct answer here, the equation we'd be solving is 256 pi equals pi integral -2 to 2 of the integrand above. This should, or it does, give us an equation in terms of k for which the volume of this region would wind up looking like the volume of the previous rotation. So if you're picturing what the two different regions look like, the first region was a little bit more like a yo-yo shape with a narrow spot at the center of the circle. And then this region, I guess, looks a little bit more like a donut. So for the 4-point breakdown on this part, you get 1 point for having the limits and the constant. So just like above, knowing that boundary. Then the integrand is worth 2 points, and they're going to subtract 1 point for each error on the integrand. And then finally, the fourth point comes from by setting up the whole equation, by realizing that we're going to be setting it equal to the first case. And as requested by my students, don't forget to comment, like, and subscribe. Smash that like button. Drop a donation in my Bitcoin tip jar.